Okay, over the last 1 week, we learned how to solve one first order ordinary differential equation. Now, today we are going to learn how to solve two first order ordinary differential equations. Once we generalize from 1 to 2, then we can go to from 1 to many. And you will see it is a very simple generalization. So let's pose our problem. We have two first order ODEs. Okay, our first ODE is dy dx is a function f of xyz. And we look at only one step process. Simply because we know if we know how to take one step, we can take many steps. And for this, we know y at xi is yi. And then we have another differential equation dz dx, which is a different function g of xyz. So we have one independent variable and two dependent variables. Since we have two unknowns, we need to have two equations. And g at xi, sorry, not g, z at xi is zi. And what we want to find is at xi plus 1, which is equispaced, what is yi plus 1 and what is zi plus 1. Okay, all right. So we covered three methods last time. Euler's method, it was order h, one function evaluation. Hume's method, order h square, two or more function evaluations. And then Runge-Kutta method, fourth order, which was order h to the power 4, and it required four function evaluations. So for solving two first order equations, we look at Euler's method and Runge-Kutta method. Both are popular methods. So let's look at Euler's method. When we had one equation, one unknown, we said yi plus 1 was yi plus h times the derivative, which was function at xi yi. Now our function has got a third argument, so we can use at the same spot xi what is zi. So naturally, when we write zi plus 1 in a similar way, it'll become h times function. Now the function is g x y z, right? Okay, let's take our example problem. Let's say we are given dy dx, which is a function of x, y, z. And our function is square root of x plus square root of y minus square root of z. And the initial condition here is y at x is equal to 0 is 1. Our second differential equation is dz dx, function g of xyz, and this function, let's say, is square root of x minus square root of y minus square root of z, and z at 0 is 0.5. So we are going to use h is equal to 0.1 and do one step. So let's make a table. xi, yi, zi. Then we'll evaluate function at xi, yi, zi. Other function xi, yi, zi. Okay. At x is equal to 0, y is 1, z is 0.5. So let's evaluate function f. So we have square root of 0 plus square root of 1 minus square root of 0.5 is 0.2929. We'll keep 4 digits. Other one, square root of 0 plus minus square root of 1 minus square root of 5.5. All right, so at next 0.1, y would be yi plus h times this value. So we'll have 1 plus 0.1 times 0.2929. So we will get 1.02929. And then 0.5 plus 0.1 times 1.7071 negative. So we'll get 0.32929. Let's do one more iteration. I hope you are doing it with me. So let's evaluate the function. So we have square root of 0.1 plus square root of 1.02929 minus square root of 0.32929. So we will get 0.7569. Okay, let's do the next one. Square root of 0.1 minus square root of 1.02929 minus square root of 0.32929, and we'll get minus 1.2721. So at next x, our y would be 1.02929 plus zero point 0.1 times 0.7569, and we'll get 1.0498. Next one would be 0.32929 plus zero point 0.1 times 1.2721 negative. So we'll get 0.20208. So my suggestion to you is please do it for 0.3, 0.4, and 0.5. Okay. All right. So on this slide, I have finished the table. Notice I'm keeping 5 digits here. So if you want, please keep 5 digits and you should match my results exactly. Let's see the next method, Rangakata method. So what did we do in Rangakata method? When we had dy dx, is equal to function of xyz. We did 4 area estimates, K1, K2, K3, K4. And then we did a weighted average of these 4 area estimates. So what we will do is, for the other equation dz dx, which is some other function g of xyz, we'll do the same thing. We'll make 4 area estimates, but give them different names, Q1, Q2, Q3, and Q4. So K1 was h times function at xi, yi, and of course we'll make it zi. So similarly, h times function at xi, yi, zi. So you'll see all we'll do is we'll keep the same arguments in both places. The function would be different. So this will become function at xi plus h over 2, yi plus k1 over 2, and zi plus q1 over 2. So same arguments here. So zi plus q1 over 2. All right. H times function at xi plus h over 2, midpoint, yi plus k2 over 2. So zi will become q2 over 2. Those are the areas for zi. Same arguments. Okay. And then 4 is the rectangle on the right edge. Xi plus h, yi plus k3, and zi plus q3. All right. Same arguments. And now we do the weighted average. Yi plus 1 is yi. 1 K1, 2 K2, 2 K3, 1 K4. Those are 6 of them. Similarly, zi plus 1 here would be 1 Q1, 2 Q2, 2 Q3, 1 Q4, and there are 6 of them. So you have all these equations here. Okay, let's do the same example as before. So even though we are going to write it in a tabular form, so we are going to write xi, yi, zi, then we'll calculate k1, q1, k2, q2, k3, q3, k4, q4. Okay, so at x is equal to 0, y is 1, z is 0.5. Okay, remember our dy dx function. Let's write it a little way down. Function of xyz is square root of x plus square root of y minus square root of z. dz dx is square root of x minus square root of y minus square root of z. Okay, So work with me. Let's do K1. Oh, H is equal to 0.1, remember? So K1 is 0.1 times the function square root of 0 plus square root of 1 minus square root of 0.5. So we get 0.0293. I'm going to keep 4 digits. Okay, then 0.1 times square root of 0 minus square root of 1 minus square root of 0.5. So we will get negative 0.1707. All right, now let's go to K2. So we'll have 0.1 times, and we'll be midway. So we'll have square root of 0.05, that's x value, plus y value, which is yi 1, plus k1 over 2, 0.0293 divided by 2, square root, minus z value, which is 0.5 plus q1 over 2, square root, and we will get 0.5 0.59, and we should have done 0.1. Let me calculate that again. So 0.1 times 0.05 square root plus 1 plus 0.0293 square root minus 0.5 minus 0.1707 divided by 2 square root, and we get 0.0594. Okay, great. Q2, 0.1 times, again 0.05 square root minus 1 plus 0.0293 divided by 2 square root minus 0.5 minus 0.1707 divided by 2 square root. So we'll get negative 0.1428. Okay, let's do K3. 0.05 square root plus 1 plus K2, 0.0594 divided by 2 square root 0.5 Q2 minus 0.1428 divided by 2 square root. So we get 0.0584. Okay, let's do Q3. Minus the y value, which is 1 plus k2 over 2 0.5 Q2 have to do that Q2 Q3 again. 0.1 times 0.05 square root minus K2 plus 0.0594 divided by 2. Q2 0.1428 divided by 2. So I get minus 0.1446. Okay, let's do K4. So this time X is 0.1. For Y, we'll do 1 plus K3 0.0584 square root, of course. For Z, 0.5 plus Q3 and we'll get 0.0749. Okay, let's do Q4. So for that, we are going to use K3, which is 0.0584 minus 0.5. We'll use Q3, which is 0.1446. And we'll get negative 0.1309. Okay, so we have got K's, we have got Q's. We put them in equation for Y, and we'll get for Y at X is equal to 0.1. Y would be 1 plus, let's do our K1, plus 2K2 plus 2K3 plus K4 divide by 6, and we'll get 1. That did not match my value. Let's see, 1.056. Let's try it again. Let's do like this. 0.0293 plus 2 times 0.0594 plus 2 times 0.0584 plus 0.0749 is divided by 6 plus 1. Okay. So I'll get 1.0566. Let's do ZI. So let's start with Q1, 0.1707, 0.1428, 0.1446, 0.1309, plus 0.5. So we'll get 0.3539. So now you take these three values and please calculate another set and hopefully you will match my results. Now here you have seen that I've kept 3 digits only. On the paper I kept 4 digits, so you can do whichever. You should get pretty close answers. If you keep 3 digits, you should be able to match my table. So please practice with it and see if you can do at least a couple more rows. Okay. Okay, so let's see where we can use this kind of two first order differential equations. Unfortunately, you have not taken sufficient technical courses as yet where you might have seen two equations, true unknowns. So let me pick up a problem from kind of social sciences, if you like, or biological sciences. But this, by the way, is the same idea that is used in modeling pandemics like this. So think of uh, your prey as being the virus and our vaccines being the predators, uh, how they model it. Of course, you may have more than one differential equation, but let's start here. So let's think about, for instance, rabbits being the prey and foxes being the predators. So let's try to model this. So we have fox, predator, and rabbit is our prey. So let's say our prey's population is YT and predator's population is ZT at any given time. So let's look at rabbits, for instance. So when we look at their birth rate, dy dt, we say it is going to be proportional to their population. And we'll assume since they have great amount of food supply, they can be fully supported. On the other hand, their death rate would be proportional to some other constant time their population. Of course, more the population, more rabbit would die. But let's say also it depends on the predator population, the fox population, ZT. Now let's look at foxes. So that is dZdt. Now, of course, they can only die due to proportional to their own population. They don't have any predators. So we will say minus C4 times ZT is their death rate. However, their birth rate would be proportional not only to their own population, but to the food. So we will say both YT and ZT. So you can see we have two linked differential equations. So we have a system of two first order equations that we want to solve. And of course, these constants could be anything, but let's say for our particular problem, we will choose our initial population of rabbits to be, say, 1,000. And initial population of foxes to be 200. And we'll use these constants. C1 is 3, C2 is 0.002, C3 is 0.0006, and C4 is 0.5. Now, of course, different constants would be in different conditions, and of course, our curves would be different. We are going to use h of 0.1, and let's say initially we'll go from t0 to 4. So obviously, we are not going to do hand calculations. So we are going to use a spreadsheet. So before we use spreadsheet, what we are going to do is we are going to set up our visual basic functions where we can put in all these k1, q1, k2, q2, k3, q3. So we have a function called p, which has got 4 arguments, h, x, y, z, and we are going to calculate 4 k's, 4 q's, and then we are going to generate an answer which is going to be a one-dimensional matrix, a row matrix, a row vector, 3 values, and those 3 values would be the next x, the next y, and the next z. Okay, so I've just typed the formulas just as I wrote it on the page before. So that's our visual basic function for implementing Runge-Kutta method for 2 first-order equations. And here is our visual basic function which is specific to our problem. So we are going to import C1 and C2 for function f. And notice here I'm not using xyz, I'm using tyz, which is our real variables, right? And this was our function. Here is our function g. Again tyz, we again import C3, C4 from our worksheet. And this is our function g. Okay. Okay, so let me bring up my predator-prey template. Okay, so here it is. Let me show you what has been done. So this is our function f. This is our function g. This is our Runge-Kutta method. Remember, it is taking in 4 arguments, h, x, y, z. We have k1, q1, k2, q2, k3, q3, and then xi plus 1, yi plus 1, zi plus 1, which we are sending back as a row vector. So let's go ahead, make sure we have named h. So that's our h. So at t is equal to 0, y is y0. This is our y0. This is our z0. And now we are going to compute our function p. Give it h, comma, x, comma, y, comma, z. Right? Sorry. Yep. Did I do that? P, h, comma, x, comma, y, comma, z. And remember, this is a row vector, so Control, Shift, Enter. Here we go. So all we need to now do is copy this till we reach about time is equal to 4. Okay, here we are. We went a little overboard, so let me delete that. Okay, so let's plot it. So we are going to plot. And let's just plot smooth curves. Move the chart, new sheet. So this is t is equal to 4. Okay, so what do we see? Our y is blue. So y's are the rabbits. So we started with 1,000 rabbits, 200 foxes. So rabbit starts increasing and reach a maximum of about 8,500 or so. The fox also start increasing in population, and notice they have increased so much to about 1,500 that they start causing the rabbit population to decrease. So they start increasing and reach a maximum of 5,000. So when we have 5,000 foxes, we don't have many rabbits left, about 1,000 rabbits left. So of course, their population would start dying off. And you can see, of course, rabbits are extinct. They all die, right? So you will see back in our spreadsheet, they have gone to 0. Now, one of the problem here is they are not exactly 0. They are some small fraction. And since numerical method is about uh, not integers, it is about continuous values, we never quite get 0. So let's see what will happen if we continue to integrate. Let's go t is equal to 12. We went too much. Maybe, why not? Let's go 3 more. So we went up to 20. So let's plot this now. Insert. Ooh, look at this. So look at this. This is all cyclic. So they just didn't go to 0. And since they are not being eaten by foxes anymore, they start multiplying. So we see that there is a lag between the maximum population of rabbits to foxes, but it is all very cyclic. So you can see it is very easy to solve 2 or more simultaneous differential equations. Okay.